Okay. Hello, everybody. We seem to have a problem, but we'll call you. Hello? I think it's probably okay now. Kalimera σε όλους. Good morning, everybody. We had some technical problems because of a high-tech projector, which also has a microphone. So I'll open my camera. Beautiful. Okay, it is a great pleasure to formally invite you to the plenary presentation, which typically takes place before the General Assembly of the Society. Give me a second. And our speaker today is Professor Hatzidimitriou, who found the time in her busy schedule because of her strong Gaia involvement to talk to us about spectacular results that Gaia has been delivering over the past few years, and in particular the ones that were recently released a couple of weeks ago with the third data release. So the title of her colloquium is The Gaia View of the Milky Way Galaxy and its Satellites. So Despina, the floor is yours, and thank you in advance.
Thank you very much. Can I be heard? Okay. Okay. So it's a great pleasure to be here with you today. Oh, can you hear me? Why? Yes, can you hear me now? Okay. So it's a great pleasure to be here with you today. And it's also a great opportunity to let you know about the extremely significant data release by Gaia, which occurred just 9 days ago, 8 days ago, actually, which I think is going to really continue the revolution that is happening in our understanding of the Milky Way galaxy and its surroundings and of galaxy formation in general. So I'll spend some time reviewing how Gaia works and what the data we get from Gaia look like, and which data are really important for our understanding of the Milky Way galaxy, although there are a lot of other applications in stellar physics, in planetary physics, and even in general relativity that I'm not going to touch upon because there's no time. So what we can learn about our home galaxy using this data, but not only, of course, Gaia data, synergies with the great spectroscopic service on the ground and from the HST and from other missions are important in putting everything together. However, the Gaia data, which is our basic theme today, is of paramount importance for understanding the structure, formation, history of our galaxy and its accretion of various other dwarf galaxies in the past and now and coming up in the future as well. So we can construct distance and velocity distributions of stellar populations of all types. We can derive the spatial and dynamical structure of the disk and the halo, study the chromodynamical evolution of the galaxy, get the star formation history. Yes. Yes, yes, indeed. It's over. Where is it? Ah, okay, sorry. Sorry, I forgot about that. Yeah. Oh, screen sharing has stopped. Okay. And I do share again. Share screen. Αυτό. Ναι, αλλά δεν είναι το σωστό αυτό. Όχι, δεν είναι αυτό. Ναι, θα ξαναξεκινήσω τώρα. Sorry. All sorts of technical problems today. Oh, good. Okay. Sorry. Okay, so now you can see me as well. Okay. So we are going to concentrate on insights, as I said, from the Gaia mission data. Τι να κάνω, παιδιά, έτσι. Is that better? No? Έτσι. I'm sharing on screen. Share screen. Κάτσε το κάνω. Δεν πειράζει, κάτσε, γιατί κάτι έγινε εδώ πέρα. Προβολή παρουσίασης. Οκ. Θα την κλείσω. Ναι, θα την κλείσω γιατί μπερδεύτηκε αυτό τώρα. Okay, so I do it again. I'm losing time on this. Okay, and then I'm going to screen it.
Πάμε στο Zoom τώρα.
Πάμε στο Zoom. Πάμε σε screen. Και πάμε εδώ. Δεν είναι σωστό, δεν κάνει το σωστό.
Οκ, εντάξει, δουλεύει, είναι οκ.
I'm sorry about all this interruption with the technical problems here with the new system. It's the first time I'm using it as well. So the Gaia mission, just very briefly, so you'll have an idea for the people that have not that are not familiar with this. The Gaia satellite was launched in 2013, and its nominal length of the mission was just until 2019. It's still working, and it's got an extension up to 2025. Eventually, we're going to get much better quality data than originally thought. So the nominal expectations are going to be surpassed by the final data release in 2030 or something like that. The orbit that it's following, it's in situ orbit around L2, which you can see here in this. Sorry. Yeah. Here in this point here, this is the Earth. And you can see the orbit more or less that is followed by Gaia. The main instruments are two identical telescopes, two photometers, let's say, that have very low resolutions, two little prisms that provide the possibility to get low resolution spectra in the blue and the red part of the optical spectrum, and the radial velocity spectrometer. I'm going to talk more about this later. The two telescopes, the two mirrors have an angle between them. You can see them here of 106 degrees. And the reason why we have these two mirrors is in order to beat down really the systematics of positions over large scales, while the design of the CCD system and the recording system, which you can see on the right here, is beating down the systematic errors on a small scale. I don't have time to explain how all this works, but it all has to do with the accuracy that we want to achieve without systematics on the positions of stars across the whole sky. So the way the instrument works is it's turning around continuously, and it's scanning the sky, both telescopes at the same time. And the data from each telescope is recorded on the same CCD. So the way that works, you can see here on this map here, I don't expect you to read all the details, but what you can see here is the whole system of CCDs on the camera in Gaia. It's the largest camera in space, actually. And you can see here the first two columns that you see here are the sky mapper columns where each telescope focuses its image. Then, as the telescope rotates, these images are traveling across the main part of the CCD, which is of the camera, because it's lots of CCDs, this part here, and they get recorded in different columns. And for each column, you get a different image. The way this is done is that the charge transfer rate is the same as the rate that the telescope rotates. So this is the way this works, and it creates all these little images that I'll show you in the next slide here. So what happens is that you get the first telescope getting stars in the first camera here. Sorry, it's the other way around now, the picture, the image that you see from the previous one. This is the first column where the sky mapping occurs, and this is where the first telescope focuses. And on the next column is where the second telescope focuses. So what you see here is images from the first telescope shown in blue, and from the second telescope shown in pink. And obviously, both of them are there on the same CCD imaging system here. And the way you know from which telescope each one came is because they come from a different column, each one. So they get marked from which column they've come, and they can be followed, and they know, and the system knows which telescope each image belonged to. And as I explained before, you get all these individual images for each column. Each column is read out, and you get all these images which are manipulated and, in a sense, quadrated in the end to get the position and the position of the system, of the star, of the object. Then the images go through the two prisms, the BP, the blue prism and the red prism, and you can see the low resolution images that you get at the bottom. And then the ones that are bright enough go through the radial velocity spectrograph, which is a medium resolution spectroscopic facility, and is used to get radial velocities and metal abundances. The important thing is that the amount of data that would have to be downloaded from space to Earth is huge. So what people do is to really cut a square around each image and only transfer and follow the data and transfer the data only for this small part. This is just a very brief summary of what is happening. It's a very complicated system, and the analysis is really complicated. Imagine that the data that are released, were released a few weeks ago, a few days ago, are only from the first 3 years, almost, more or less 3 years of operation. And we're already, from 2013, 8 years ahead. So the data analysis is really extremely heavy. And this needs to be taken into account. It's not an easy job to get micro or millisecond accuracy in positions. So now what I'm showing you here is what you get if you just project on the sky map, just the amount of transits you get for all these little images you get, the amount of transits you get without taking into account if they are stars or whatever they are. And this is the distribution you get on the top left on the screen. And these peculiar shapes that you see here are have to do with the way the instrument works. The orbits, there are specific areas in the sky that are covered with more exposure. So that is what is shown here. If you correct with the scanning law of Gaia, which is the second picture on the right, then you get the map that you can see at the bottom. So this is not a source map. It doesn't have individual sources. It's a density of, it shows the pattern of how many data have been amassed during the, actually this is for more than 3 years. This is a longer period. This is until a few months ago. So as I said, the data processing and analysis is very heavy. And there's a consortium which is called DPAC, Data Processing and Analysis Consortium. And you can see it's a pan-European effort, and we are a small part of it. The work started, the collaboration started in 2006 by Milky and a group at the Observatory of Athens, led today by Yannis Belavelidis, who started this collaboration. And now we are continuing both with Yannis and Mary and other people and myself here at NKUA. I don't want to sort of spend too much time explaining how this works. You can see that it has all sorts of different modules. Different modules work on the photometric processing, on astrometric processing, on spectroscopic processing. And then there are special modules that work with specific types of objects. For example, we are involved with the extragalactic sources, galaxies, and their classification and redshift determination. And this is our part of the data processing. And I should say that in Gaia DR3, it's the first time that we've got data released about the galaxies. I'm going to show you, although it has nothing to do with the galaxy, with our Milky Way. At the end, if I have time, I'll show you some of the results that we got from this module. CU8 is not just for that, it's also for all the astrophysical parameters of stars. And I'll show you results, extremely significant results that come out from that part of the module. The data releases I show you here are started 3 years after the Gaia was put into orbit. Then it's DR2 in 2018, which already showed very significant results. DR2 had radial velocities as well as proper motions and parallaxes. EDR3, which was released in December 2020, early data release 3, had significant improvements on parallaxes and proper motions, but it didn't have radial velocities or any other new information. And now we have the full data release 3 with everything improved in EDR3, parallaxes and proper motions, but nothing new on that side. And additionally, stellar parameters, astrophysical parameters, and as you see, lots of other data. Oops, what is that? And these are the people that are involved in CU8, just our module. You can see some faces from Athens here. So what do we do with all this? What is the information we get more or less? We get 5-phase space components, position, two components of the position. One component is parallax, and 2 components are the 2 components of the proper motion, PM and PM deck. And we get these for millions, hundreds of millions of stars. Of course, you know how this works. I don't need to explain that. What is more interesting to show is the accuracy that we currently have on the parallaxes and proper motions and positions. And what you see here on the right is the distribution of accuracy for positions, for parallax and proper motions, and you can see clearly the orbital, let's say, characteristics and the coverage of the scheduling, let's say, characteristics of the telescope. This is going to improve with time, so at the end of the mission, these features will be less obvious. And you can see here on the left the uncertainty of parallax versus magnitude, and you can see that for nearby stars, the parallax accuracy is very good. You have a parallax accuracy of 0.1, 0.01, 0.02, 1 to 2% milliardsecond. So you have microarcsecond accuracy in parallax. And that's going to be improved with time towards the end of the mission. Then the next, as I said, after the astrometric part, we go on to the spectrophotometry, which has the medium resolution spectrographs with the prisms. And this is a picture that shows the spectra of different stars as a function with different temperatures as they are produced by the blue and the red spectrograph, the red prisms, the spectrophotometric instruments of Gaia. And on the top, I show you the 3 filters, bands, let's say. They're not filters, they are bands that construct magnitudes in BP, RP, blue, red, and the G magnitude, and all the CM diagrams, HR diagrams that I'm going to show you are based on these 3 bands. Somebody had a question? So a hand raised? No.
There is a question
On chat? Yeah, maybe at the end. Yeah. Because we've already lost a lot of time. Yeah. So the next thing I want to show you is an example of an HR diagram that you can construct using these 3-band data, G, BP, and RP. And this is a CMD in the Large Magellanic Cloud constructed from Gaia DR2 data. Now we have more information, and you can see on the right the distribution of stars that are used for the CM diagram in space. This is taken from Yuri et al. 2021. I should say that we use this data a lot on the Magellanic Clouds, and I'm probably going to show you some of these results later this time. I show you here some astrophysical parameters. As I said, we use the low resolution spectra to derive basic parameters for stars. I didn't show them here. And these include temperature, surface gravity, extinction, mean metallicity, and radius and distance of the stars. Of course, we use the parallax information for that as well. And for some objects, we also get ages and evolutionary stage. So all these parameters are available now for millions of stars in our galaxy and in nearby galaxies. So here I just show you an example of these of the usage of such parameters. This is the absolute magnitude that you get from the apparent magnitude, obviously, and the parallax information, and the temperature that is derived from the astrophysical parameters in for about 470 million stars with G less than 19. The next instrument that the images pass through is the radial velocity spectrograph, which has a medium resolution spectrograph from which you can get metal abundances for all these different elements I show you here. And of course, radial velocities. So we get radial velocities and abundances, and also other astrophysical parameters similar to what we get from the low resolution spectrograph, but for brighter stars. The formal precision we get for velocity is about 1 kilometers per second for bright stars, and about 6 kilometers per second around 14. This is the distribution. If you imagine that we are at the center here, this is the sun, the center, and these are the stars for which we have radial velocities. in the sky. Obviously, as you go further away, the density of stars we can observe, because our data set is flux limited, is much smaller. This is another very interesting result that came out from the DR3 data. What you see here is a distribution. Again, it's a similar plot to what we saw before for the radial velocities, but it is for the diffuse interstellar band at 862 nanometers. This is this little band here, this diffuse band of interstellar absorption. We can map this interstellar absorption out to a few kiloparsecs from the sun, and this is very important for understanding of the interstellar medium in the disk of the galaxy near the sun. Here, I don't expect you to be able to read all this information, but it's only a small part of the information that is available now in Gaia DR3. There are about 40 different tables that give you information about millions of sources from stars, galaxies, quasars, planets, binary stars, variable stars, and also for meteorites, planetesimals, and all sorts of other objects in our solar system. So it's a huge data set. I don't have time to explain all this, but everything is available in the Gaia DR3 site here. I give you the address in case people want to have a look at it. So let's have a look at some highlights from Gaia on our understanding of the galaxy. We're going to look at some global properties that we get from, especially from the DR3 data, results on the disk structure, spiral arms, and something that is only came out from the Gaia data, the so-called phase spiral. I'll explain what that is in a moment. Star formation history, halo substructures, and accretion history, both from Gaia DR2, EDR3, and from DR3. So this is the first glimpse of highlights of the Gaia DR3 for the global properties of the Milky Way. I'm probably going to say more about this later, but quickly, this is a radial velocity map. So you get radial velocities with respect to the sun for millions of stars, about 30 million stars, and black, with black or darker colors are objects that move away from us, and brighter colors are objects that move towards us. And this peculiar wave that you see, dark, bright, has to do with the motion of the sun in the disk of the galaxy and the rotation of the galaxy at the same time. At the bottom, you see the same picture, but the colors are now, for the radial velocities, are blue and red. And the flow lines that you can see come from the proper motions of the stars. So you can see the space motion, in a sense, in this plot of the stars in the sky. On the top right, you can see the distribution of AG, which is the extinction in the G magnitude for billions, hundreds of millions of stars in the galaxy. And you can see really the dust lane as you expect, of course, in very much detail. And at the bottom, you can see the metallicity distribution of the galaxy. This is an extremely interesting result, which needs a lot of explanation, because one has to be very careful how one interprets this result. One needs to take into account the systematics that get into getting these images. So if I have time, I'll explain more about that in a minute. One of the very interesting results, so the rest of the talk is going to be some highlights that I sort of found very interesting, but it's only a choice. There are hundreds of papers, very interesting papers, actually thousands of papers in the last few years that are based on Gaia data. And there's no way one can really cover everything. So I sort of chose a few very interesting results for our understanding of the galaxy, and I'm showing these here. So this is from work by Popeskov et al. 2020, and what they did was they used the data from Gaia DR2, for which at the time there were available radial velocities, and you can see the distribution of these stars. Here it's the same plot that I showed you before. At the center is the sun. This is more or less the bar of the galaxy. And what they did was the following. Imagine that you can probably look at the plot at the top right. Imagine that we are here at the solar system and we observe the spiral structure of the galaxy. This is, of course, a sketch. It's imaginary. So you can both observe over densities across the line of sight, and you can also measure velocities, radial velocities. You can also see a variation in the radial velocity field, which is projected. It's the velocity, spatial velocity projected along the line of sight. So what they did was to use this data to create these density maps, which look a little bit peculiar if you look at them, but what they've done really is to use a different coordinate system, which is called, this is the spatial system, let's say, the spatial coordinate system, and this is the so-called guiding coordinate system, which is described at the bottom here, and it's related to the motion of the object around, the rotation of the object in the disk. If there are questions about this, I can explain later in the question time perhaps, but what I want to show you here is that you can clearly see different overdensities that are also related to radial velocity signatures, as you can see here. And these overdensities are, it's the first time we can actually see the spiral arms in the whole population, for all populations basically, and not just for gas and very young stars as has been done until now, because this is everything, all stars in the disk, all stars that we can see from the sun, and have radial velocities for, and you can see the imprint of the four main structures, spiral arms, in the total population, the global population of the disk. And this is the first time that this has been shown. There are also indications of different overdensities that are caused by the limb blood resonance, for example, around 9 kiloparsecs, which is down here, and the corrotation radius resonance here at 6 kiloparsecs, 6.5 kiloparsecs. So this is a very important result because it's the first time that it has been shown in detail. And I think this is going to be repeated now with the many more data from Gaia DR3, which extends to much larger distances, and it's going to be very interesting to see how this result will hold with new data. Another effort to trace the spiral arms was done with the Gaia DR3 data using astrometry and integrated photometry. That was published by Poggi et al. In 2021. And also you can see here the overdensities with the 4 different spiral arms shown here as overdensities. I don't have time to go into details into this. And I would like to spend some more time to explain the famous now Gaia phase spiral that was discovered almost by mistake, by serendipitously, let's say, in 2018 using Gaia DR2 data. So what they did was to just plot the vertical velocity. So we have the disk, we have the vertical velocity at Vz is perpendicular to the disk, and z is the distance above the disk or below the disk. So if you do that for all the stars that you can get velocities for, so for this tier 2 sample of million stars, you get this very peculiar plot if you actually colored it with V phi, which is the azimuthal, the rotation velocity. So this was really a surprise. Nobody had predicted something like that. And it's actually quite simple. It's phase mixing that is caused by perturbation. If something falls through, something big, like a big dwarf or another galaxy falls through the disk, it sort of creates a splash And the objects in the disk start oscillating up and down. And the period of the oscillation has to do with the distance from the center, which is like the length of the string, if you can imagine that, and the amount of mass you have in that structure there. So you have different periods at different distances and different substructures. And since you have different periods, as this thing rotates around the center of the galaxy, you get phase mismatch and you end up with a spiral thing. So it's a phase mixing effect in a sense. This is extremely interesting. And actually, if you look at the distance between two subsequent spirals, like this, for example, this one, for example, this one, and this one, and this one, if you assume some basic stuff about the basic model about the dynamical, the potential of the galaxy, you can actually find how much time when the splash occurred. And when that was done, it was found that it occurred a few hundreds mega years ago. And it is very interesting that this same time coincides with a close passage of the Sagittarius dwarf. So one of the favored explanations for this oscillation of the disk up and down is probably the close passage of Sagittarius. However, if that were the correct explanation, Sagittarius would have to be much more massive than we know it is. So there's something else going on, or Sagittarius was much more massive then than it is now. There have been lots and lots of papers, theoretical papers and observational papers on this, but I chose to just show you the original work by Ando Haidar in 2018. That was a Nature paper. This is just a sketch that shows you how this works. So if you have this displacement I talked to you about due to the splash in a certain location, you get the stars moving down, and they rotate around the center of the galaxy. If you proceed and you see how this will, as they oscillate up and down, they sort of, depending on their period, as they turn around the galaxy as well, you start having this phase mixing I told you about, and in the end, you end up by a spiral looking like this spiral here. So this is just a sketch that shows you that this idea is meaningful. Now moving to the next subject I wanted to touch upon is using the amazingly accurate and complete CM diagram that you can create from the data from Gaia, because you now have distances to the stars, so you can really create a very good CMD with millions of stars, and you can see all sorts of different aspects of stellar evolution that I'm going to get. I don't have time to get into that. I just mentioned very briefly that for the first time it was possible to see the phase for the crystallization of white dwarfs, and that was achieved with these amazing data in white dwarfs. But that's a different story. I don't have time to talk about that. Using these data, you can use models of stellar evolution and create a star formation history of the galaxy, of course, around relatively nearby. And this is star formation history you can get near the sun within the 2 kiloparsec bubble around the sun. And you can see, that's a paper by Ruiz Lara et al. 2020, and you can see that there's a large peak of star formation around 5 point something gigayears ago, and later in these different periods of time, and this one as well. And they all seem to be coincident with close passages, perigalactic passages of Sagittarius, on the Sagittarius dwarf. And this is the last one that coincides with this phase spiral that I showed you before in terms of time, when it happened. So this diagram really shows you the star formation history that was had a much higher efficiency in the past. It was quite low up until about 5 gigayears ago, where it really increased by a large amount, and probably this increase is related to star formation that is induced by the passage of probably the Sagittarius dwarf, and you can see these other peaks here as well that are probably related again to Sagittarius. There's a very interesting paper that came out in Nature just a few months ago, which really derived some extremely fascinating results about the star formation history of the galaxy. And unfortunately, I don't have time to go into much detail, but I would like to point out that using this method, it was possible to show that the thick disk, the old disk in the galaxy, actually formed almost 0.8 gigayears after the Big Bang, 13 gigayears ago, 2 gigayears older than we thought before, and it preceded the intergalactic halo. The intergalactic halo final assembly occurred about 2 gigayears later, around 11 gigayears ago. So this is a fascinating new result, and I'm really very curious to see what the new results from Gaia DR3 will show about this. What they did is, just briefly, they used this part of the CMD, some giants, this part of the CMD, and models that to get ages from these subgiants. And they also use radar velocity information, because in order to decipher what's happening, they had to use the information about the not only the position and the velocity, but also the angular momentum of these stars. This is a plot of Fe over H, the metal abundance, versus age that they got from the models that they used, the Basti models, I think. And the red dots are from previous measurements from the literature, and you can see the huge amount of data we have from Gaia DR2. Imagine what it's going to be like with the Gaia DR3 data. So this is a fascinating new result. And I go on with age distribution, since we talked about the star formation history, showing you here the map, the sky map of the ages that we derived using the astrophysical parameters module of Gaia. 0 is dark blue, and 13 gigayears old is red, and you can see the distribution of different ages in the sky. And I think this is a really fascinating result. It includes 130 million measurements of ages in the galaxy from Gaia DR3. This is the same plot I showed you before about the metallistic distribution of the Milky Way, which looks really fascinating when you look at it. You can see all the metal-rich stars, which are the red stars, are in the thin disk. And then you have less metal-rich stars in the center, around here, and also at the edges of the disk. However, how you interpret this plot has to do with the fact that all the stars you see here are all stars at all sorts of distances from the sun. So you can derive the wrong conclusions if you don't take that into account. So in the next plot, although this is a very interesting plot to look at it, but in the next plot, you see what happens in the same plot if you cut slices in distances along the line of sight from us. Okay, so these are the very close by stars, and you can see they are all very metal rich. So they are solar abundance, more or less. And as you go further away, you start moving towards the disk, thin disk, and we have all these features here, thick disk or flaring of the disk. And then you move to the very far away stars, and you get thick disk and stars that are related to the halo and so on. So really you need to do cuts like that and use all information that is available in order to interpret this beautiful plot that I showed you before. I had this discussion with a colleague a few days back, and it's not an obvious thing. You look at it, but you really need to think a lot about it to understand what it tells you. This is a plot that is also fascinating. It's a plot of alpha elements over iron. for a few million sources for which alpha element measurements are available from the radial velocity spectrograph. And you know that this ratio is used to identify stars that are formed in galaxies with a different star formation history, or in the same galaxy at different stages of star formation. For example, thin and thick disk in our galaxy, or halo and thin and thick disks, have different A/Phi elements. And this is something that is expected to show very important results when it's analyzed properly. I should just say that these results, these features here are not real. They have to do with the fact that when Gaia started to observe, they started close to the ecliptic, and they have a lot more observations along the ecliptic, so much higher signal to noise, which means they get radial velocities and spectra for much fainter stars. So you go further back and you see different alpha element abundances. So these features are not real, they're not features in the galaxy, they have to do with the signal to noise as a function of location in the sky. And this will be obliterated at the end of the mission, I believe, when the signal to noise is increased everywhere. So don't think that these are streams or something like that. So one needs to be careful how one interprets the results. And very interesting results that came out just a week ago is when you look at this feature, this phase spiral I showed you in the previous few slides back in metal abundance, you see that this is metal abundance color here. You can see that the spiral is also related to metal abundance. Now, how that is going to affect our theories about how this is formed, I don't know. I don't know the answer to that. But it's difficult to explain it with just the phase mixing, I think. And we have to see what comes out of that. Then plots of A/Phi, the alpha elements over iron versus metallicity, together with kinematics, have been used to identify streams and remnants of dwarf galaxies that have been merged with the galaxy in the past. And these are some plots, again, that came out a week ago for the 4 major objects that we know that merged with our galaxy in the past: Gaia Enceladus, Thamnos, the Helmi stream, and Sequoia. And I should also mention here that just very, very recently, there's been a discovery of another stream. This is the C19 stream that you can see here, which probably seems to consist of pristine stars. So it must be the oldest structure in the galaxy, or that ended up in the galaxy. This is a fascinating result that used Gaia and CFHT data. Now, using conserved quantities such as energy and angular momentum, you can actually isolate in this space of angular momentum versus energy objects, stars that belong to similar entities, similar structures. So all these sort of delineate different structure, kinematical structures that probably belong together in the past. And what you see, this is from Helmi 2020, and that's how you actually find all these peculiar remnants, relics of structures from the past. And what you see on the left side, I'm going the wrong way here. On the left side, you see various streams that are observed using these different groupings here, and the same colors are used for these colorings here, and you can see how the streams follow these conserved quantities here. You see that it's a total mess. I mean, there are streams that are formed from globular clusters, from other star clusters, from dwarf galaxies that go through the disk of the galaxy and get destroyed. And these are all the remaining streams that you get from all this situation. Now, another, I have to hurry up, another very important result has to do with the halo, the stellar halo near the sun, that seems to be, what you see here is the velocity, prograde velocity on this side and retrograde velocity on this side versus the radial velocity here. And you can see that this is the disk, this is the hot thick disk, and you can see there's a whole bunch of stars that are retrograde in their rotation, and they all seem to belong to this feature here in the alpha over Fe plot. So they are obviously a separate entity, which is the so-called Gaia-Enceladus dwarf, which really comprises the largest part of the local halo near the sun. So these are various streams that were found with Gaia in the galaxy. And I'm going to just show you a very brief result that has to do with the center of the galaxy, although with Gaia we cannot see the center of the galaxy. It's very obscured. Gaia looks at the optical wavelengths. But what was discovered very recently, it's a paper by Prof in 2019, is an extremely fast star with this orbit that you can see here, with a velocity of around 1700 kilometers per second. That must have been the best explanation is that it was formed by the so-called Higgs mechanism when a binary interacts with a very massive black hole. One of the binary constituents sort of gets kicked with velocities that for a massive black hole like the one that we have in the center of our galaxy can give you velocities up to 4,000 kilometers per second. So this is just a fascinating result that was published in Nature a couple of years ago, 3 years ago. So let me show you now results on the Magellan Clouds to close. Unfortunately, I don't have time to show you all this. I should say here that using the perturbation that is observed in one of the streams in the galaxy, that is observed in the galaxy, and trying to understand why this there's this curve in its shape. If you take into account the LMC, you can sort of start explaining the shapes you see here, but you have to assume that the LMC is about 10 times more massive than what we thought it was. So these are all very important results about the masses and the total mass of the local group, which is probably underestimated by quite a significant factor. These are lovely pictures of the Magellan Clouds, which are my pet galaxies, so I could not resist showing these to you. We work now with the new data from DR3 on the LMC, basically on the SMC. What you can see here is that the SMC is in big trouble. We've known that for a while, but we never imagined that the whole galaxy is moving towards the LMC. I don't know if you can see the proper motions towards this direction, which is the direction of the SMC, the LMC. I don't have time to show you these. These are new results that are coming out now. And just as promised, I'll show you the distribution of galaxies with redshifts that we got from our module, UGC, the CU8 module that we work on here in Athens. And the redshifts we get up to approximately a redshift of 0.6 are shown here as a function in the color diagram. And here I show you comparison between the SDSS redshifts with UGC redshifts for common objects. And you can see the redshifts we get using machine learning and the regular distribution spectra are quite good, with an average error that is acceptably small, 0.1 or better. So unfortunately, I have to stop because I've already took too much time. So to sum up, Gaia has revolutionized our understanding of the Milky Way galaxy. There is a lot more to come. We can claim we can now reverse engineer our galaxy almost. And I think in the very near future, and by the end, definitely by DR5, the final data release, we are going to have deciphered the formation and evolution of the whole local group owing to this data. Thank you very much.
Thank you very much, Despina. There is a question from the audience online. Κυρία Γλυνού ρωτάει πόσο επηρεάζεται η Gaia από τις εκτινάξεις μάζας από τον ήλιο που ακούγεται πως αυξάνονται τελευταία.
I'm not aware of any particular problems because it's quite far. It's at the Lagrangian 2-point. So I'm not, and it's not, for the moment at least, there is no information there is any big problem with that. I mean, the shielding that is available for the instruments is doesn't cause any alarm for the moment. But we'll see. I don't know. There's no information about problems of that kind of.
A question from Adonis Georgakakis.
I have questions actually. The first one is on this streams plot which you saw, where there was a colorful plot with the conserved energy quantities plot, and you have color coded there clouds, but it's not clear to me how the color coding has been
actually
assigned to those data points, because it's obvious that
goes the other way around.
From these plots, right? So they have been identified in a different way, and then
sure, it's, as you say, they are identified as groups more or less here, and also in the alpha element, in this energy angular momentum plot more or less. And you also.
So my question is, there's a lot of overlap, right?
Yes.
So the color coding has come from somewhere else.
Yeah, you have color coding from this energy angular momentum, which is a very basic thing to show you that there's this idea behind that when stars belong to the same original object, because of conservation of energy and angular momentum, you can identify them there. But that's not enough. You identify them in spatial, there's a spatial coordination, which is not shown here. And there's also, in many cases, metallicity coordination, alpha element signatures, let's say. So it's in reality, it's location, kinematics, and metallicity that are used to isolate them. So this is a bit of a nice picture, but there's a lot going into creating it. Yeah.
And all those correspond to informing structures.
No, not necessarily. It can be clusters, star clusters. I didn't show you that. For example, I don't have that.
Oh,
yeah,
so
I thought I had. Yeah, I thought I had a hidden. I have one that shows the. Let me show you. Just give me a second. That shows these traces of clusters, star clusters. I hope I have it here hidden. So here it is. So I have to show it on the slide. No, let's see here. Oh, I cannot see it. I have to go here. Here. So these are streams that are related to globular clusters. So they follow the orbits of the globular cluster. We have proper motions and radial velocities. So we can build the orbit of the galaxy. And you can find the stars that have the same signatures with the globular cluster following these streams. So this is probably easier to understand than the previous plot.
Sure. So it's one of the last plots where you saw the galaxy center. So the questions about the redshifts. You mentioned machine learning.
I should tell you.
Are those? It's okay to read. Those are photometric redshifts, or are they coming from analysis of the spectra?
Yeah.
Which are low resolution.
Yes.
You need some analysis.
Yeah. We use both the blue and the red low resolution spectra. What we do is a neural network machine learning method, and we assign redshifts to spectra of galaxies from SDSS that we know the redshifts for. What I showed you here for a comparison is not with the same objects, obviously, because it would be crazy to use the same objects. You use a subset for testing, and the rest, for teaching the program, okay, for learning. So we use this machine learning technique to assign redshifts to the various objects. That was a lot of work that went into that to beat down the systematics and find systematics. There are all sorts of systematics that are related to the way that Gaia observes. What I showed you, if you have a galaxy, it's an extended object, and it goes through this thing. And the galaxy is not like a star. It has features, it has central concentration, spiral arms, blah, blah. So when you go through, for the close-by systems, when they go through, depending on where they are, and given that the system, if you remember, cuts a square around the maximum light, it can get a maximum light at different parts, and you get errors from that, quite significant errors. So for the very close by objects, this is worse. And you have a systematic problem in very, very low, nearby objects. And that will not go away. But it will be really decreased as you get a lot more passages, because as you get more and more and more passages, this effect will sort of average out and disappear. And think that we only have 3 years of data. We have how much? 11 years, or 12 years of data. So 4 times as much data as we have now. Hopefully, if all goes well at the end, eventually. Because these data are based on 3 years data only. Third question.
The accuracy of the agents are not good enough to see the cosmic web.
Yes, you can. Yes, you can. In areas where you have here, where the pattern is not so bad as here, you can see the cosmic web. I don't know if I can.
Now you just see the scanning of
No. Here, up here, if you look at this part, okay. Unfortunately, I don't have a. Yeah. If you go inside the area where you have a lot of passages and you look only there, you can see the cosmic web. Right. You definitely can. But actually, we had created a plot showing it, but we decided not to, because the scanning law and the systematics are so heavy right now that it's not correct, I think, to use it yet. Not for, but it shows you the potential for the cosmic web, I mean. Or you have to be extremely careful which areas you use. Yeah. And you can see here, you can see the Magellan clouds, and they shouldn't be there. Also, there's some problem where you have overcrowding. There are leftovers here. There are some leftover things there. For example, the system thought that there were galaxies, lots of galaxies in there, but there weren't really. So when there's overcrowding, there are problems. So we had to take, the validation took years.
Yeah.
Okay, so it's not an easy job. Yeah. So.
There is a question by Manolis Xilouris. Says, how does the extinction map you showed compare with the Firby-Kobe maps?
It hasn't been, for the moment, they just show the result. It hasn't been in detail analyzed yet. This is only 7 days old. So there's lots to be done.
I don't know if there is any other question from the audience in the room. If not, I would like to...
I have a question, sorry to interrupt you. I have to raise my hand. Hi. Hi, Despina. So thank you, it was a very interesting talk. So I would like to ask a question about
Yorgo?
Yes, can you hear me? Despina?
No, Yorgo, why don't you tell me the question and I'll hear it. I'll hear it. I will definitely hear your question. I will just pass it along.
Okay, can you hear me so you can pass my question?
Yeah, I can hear you.
Okay, so my question is, okay, I'm interested in high mass in X-ray binaries, and finding accurate distances is important. So looking from DDR for data release 2 to data release 3, we noticed for some systems a very large improvement in the errors, which I don't know if it's justified by the X.
Up until that point, Despina Yorgos is suggesting, is saying that analysis that they've done on distances of high mass X-ray binaries going from the previous release up until now releasing the present release appears to be substantially more improved. Why is that? I presume. Is this your one?
Yes, actually, my question is like, how much can we trust the statistical uncertainties?
How much can we trust the statistical uncertainties? That's the question. For distances.
Whether correlations, there are systematic correlations for distances, and you have to look at there are papers that have been published that suggest corrections that you have to apply. So corrections are not applied in the published results, but you have to read the papers. So there are specific recipes that have been found from additional cross validation, and there are recipes for corrections of systematics in addition to what has already been done. And you can choose to apply them or not apply them and see what you get. Okay. So definitely you need to be careful. You need to read the papers in very much detail before using the data. And I really want to stress that. You don't just go and use them. You have to know what you're using.
Okay.
Okay, thank you. I can ask later for details.
I don't see any other raised hands. So if not, I would like to thank Despina on behalf of all of us again. And you muted me now, Despina, but it's okay.